Welcome everyone. Today's session is building an AI agent with .NET Core and Ollama. A practical code-first workflow for C# and .NET developer. We'll spend about 20 to 13 minutes covering four things. The core concept behind AI, LLM, and agents. Why and how to run model locally with Ollama. How to wire all of that into a real ASP.NET Core web API. And a look at the wide ecosystem. Memory, RAG, tool calling, MCP, and multi-agent system. By the end, you should be able to be back to your own machine, install Ollama, and be a working agent endpoint in C# within the hour. That is a hand-on engineering talk, not a theoretical AI lecture. We will look at real C# codes and a live Swagger demo along the way. Let's get started. Here is the roadmap. We have grouped the ninth topic into four parts, so the session has a clear arc. Part 1 is foundation. What AI, agent, and LLM actually are. Plus, a look under the hoods of transformer at intention, and a comparison of today major model family. Part 2 is about running model locally. Why you would want to, and how Ollama make it simple. Part 3 is the main engineering block. We design the system architecture, call the Ollama REST API from C#, build a small ASP.NET Core agent, and run a live Swagger demo. Part 4 cover the concepts that turn a simple agent into a serious one. Memory, prompt engineering, retrieval augmented regeneration, tool calling, MCP, and multi-agent system. Before we close with best practice, use case, and recap. Feel free to hold a question for the end, or drop them in chat if it is a virtual session, and I will address the comment one during the wrap-up. Let's start from the top. Artificial intelligence is a broad umbrella term for any system that performs tasks with normally associated with human intelligence. Reason, perception, planning, language. They included very old technical, like rule-based accepted system and search algorithmic. Not just modern neural network. Machine learning is a subset of AI, where instead of hand-coding rule, we let the system learn pattern directly from data. Deep learning is a further subset of machine learning that use multi-layer neural network, which is what made the current wave of AI possible. That model learn very complex pattern from huge amounts of data, and generative AI, including the large language model we are focused on today, is a deep learning approach of speciality aimed at generation new content, text, code, image, rather than just classifying or prediction a number. Everything else is they stalk life inside the innermost circle. We are building application on top of generative LLM-based AI. So what makes something an agent rather than just a chatbot? A plain LLM call is stateless and single shot. You send a prompt, you get text back, done. An agent is built around a loop. It perceives, take in input, whether that user message, a file or data from an API. It reason, use the LLM as the decision-making engine to figure out the next best step, not just to produce a final answer. It acts actually call tooling, function, or external API to do something in the real world, like querying a database or sending an email. And then it observes the results and loop back around, adjusting its plan. That loop perceive, reason, act, observe is what we mean by an AI agent, and it's the mental model to keep in your head for the rest of this talk. Everything we build in the C# demo later is a minimal one-step version of this loop, and the advanced topic near the end. Memory, tool, multi-agent are all about making this loop reader. Zooming into that loop, here is what a real agent architecture look like. User inputs come in at the left. It hits the orchestrator, the LLM reasoning core, which is the brain of the operation. It decides what to do next given the current input and everything it knows so far. That orchestrator doesn't work alone. It leans on their supporting pillar. Memory holds the conversation history and any long-term facts the agent needs to remember across turn. Tool and action are the function and API the agent is allowed to call. This is what turns the model has an opinion into the model did something. And knowledge often implemented as RAG, retrieval augmented generation, supply grounded up to date, or private information that wasn't in the model training data. The orchestrator pull from all three as needed, then produce the final response output. This is the architecture will be on showing later is our ASP.NET Core design. The AI servers in our C# code play the role of the orchestrator. Now, let's zoom into the reasoning core itself. The large language model at its core, an LLM is a neural network with a huge number of learning parameters, often in the billion, that encodes statistical pattern about language. It gets those patterns by training on enormous datasets, typically measured in trillions of tokens of text and code scraped from book, websites, and other sources. But actually mechanical tricks it perform over and over is deceptively simple. Given some text so far, predict just the single next token. That's it. There is no separate understanding step and writing step. The entire generation process in the one operation repeated thousands of times per spans everything interesting the model does. Answering question, writing code, holding a conversion. Emerge from chaining together next token prediction. Will impact exactly how that works over the next three slides. Tokenization, the transform architecture with attention, and the prediction loop itself. Before any neural network might happen, text has the bank, text has the become number. That's tokenization. Here we take the phrase building an agent and break into subwork token. Notice building, split, and build and eng model don't tokenize words. They add subwords into unit so they can represent any words, including what one never seen during training, made up words, or code identifier. By combining small pieces, each of these tokens map to a fixed integer ID from the model vocabulary. Essentially, a look table with tens of thousands of entries. Those integer ID are then converted into embedding vector, long list of number, often several hundred dimensions, that capture the token meaning in a way the network can be do math with. Similar meaning and up as NURBY vector in this high dimension space. This token is then embedded. Step happen on both your prompts and, as we'll see, on every token the model generated. It's also directly relevant in practice. It's why LLM API bill per token rather than per word or character, and why prompt length limits are expressed in token, not words. Once we have embedding, they follow through the transformer, the architecture behind essentially every modern LLM. On the left, you can see the structure. Embedding go in, then pass through the same block repeated many times. Sometimes dozen in time for large model. Each block has a self-attention step, a normalization step, a feed-forward network, and another normalization step. After the last block, the network produces output probability over the vocabulary. The key innovation is self-attention shown on the right. For every token, the model computes how much it should attend to or write every other token in the context when building its representation. In this example, the word agents pay a lot of attention to AI, a moderate amount to building, and very little today. Breather and Decker line represent strong attention weight. This is what lets the model handle long rank dependency, pronouns referring back to the known several sentences early, or code where a variable is used far from where it's declared. Attention is computed freshly for every token in parallel, which is also a big part of why transformer training efficiently on modern GPU. You don't need to implement this yourself. Ollama and every model we'll discuss already have it built in, but understand it helps explain model behavior, why longer, well-structured context tends to produce better answer, and why relevant text in your prompt can dilute attention away from what matters.